Hello, welcome to lesson 35. So you'll want to make this correction on your slides if you printed them out. This is actually lesson 35, not lesson 33. And we're going to be doing an inference review. So we have some instructions. Answer each of the following questions using either a hypothesis test or confidence interval. Where appropriate, be sure to give the hypotheses, point estimate, standard error, test statistic, and p-value. These problems were taken from Collaborative Statistics by Barbara Ilowsky and Susan Dean. Here's example 1. Okay, a powdered diet is tested on 49 people, and a liquid diet is tested on 36 different people. Of interest is whether the liquid diet yields a higher average weight loss than the powder diet. The powder diet group had an average weight loss of 42 pounds with a standard deviation of 12 pounds. The liquid diet group had an average weight loss of 45 pounds with a standard deviation of 14 pounds. So let's write down some things that we know from this example. We know that there are 2 samples, and we know that we're dealing with means. And we know that this is unpaired data. So remember that unpaired data means that we have 2 separate groups with no relation. Alright, so here is the table that shows those summary statistics. So let's go ahead and write down the hypotheses statements. So the null hypothesis would say that the average of the liquid diet minus the average of the powder diet equals 0, meaning there is no difference. And the alternative hypothesis would say that the average of the liquid diet minus the average of the powder diet does not equal 0. So we do have a point estimate here. And symbolically we would write that as x bar L minus x bar P. So the x bar L is 45, so we would take 45 minus x bar P, which is 42, and we get 3. So our point estimate is 3. We can also calculate the standard error. Because this is a difference of means, we would look up the standard error formula for the difference of 2 means. So this is going to equal the square root of standard deviation for the first one, 14 squared, divided by the n for the first group, which is 36, and then we subtract the standard deviation for the second group, squared, divided by the sample size of the second group, so 49. And when we type all of that into the calculator, we get approximately 2.895. Next, we can calculate the test statistic. We will use a t-value because we're dealing with means. So we're going to be using a t-distribution. And we'll take our point estimate 3 minus our null value, 0, all divided by the standard error, which is 2.895. And this gives us a test statistic of approximately 1.036. So if I were to draw a t-distribution curve, where 0 is in the middle, if I mark off where 1.036 is, it might be about right here. And my p-value would be all of the area under the curve shaded to the right, but also equivalently on the other side, everything to the left from negative 1.036 and to the left. The degrees of freedom equals the smaller sample size minus 1, or the smaller group size minus 1. So that would be 36 minus 1, which equals 35. So we can calculate the p-value using the tcdf command, and we would have 1.036, 999, 35, and we do multiply this by 2 because we want both tails. And so this gives us an answer of approximately 0.307. Now this number is greater than our significance level of 0.05, so that means that we would fail to reject, let me try that again, fail to reject the null hypothesis. It means that we don't have any evidence of a difference. Now we do want to be cautious about these results because we can't check any conditions. In other words, we don't know if these samples are random samples. So I'll write that down. Now let's take a look at example 2. It says, at Rachel's 11th birthday party, 8 girls were timed to see how long in seconds they could hold their breath in a relaxed position. And 2 other girls passed out. That's not good. After a 2-minute rest, they timed themselves while jumping. The girls thought that the jumping would not affect their times on average. Test their hypothesis. Okay, so let's write some notes here. So notice that these are the same girls in both groups. So this would have to be paired data. All right, so let's write down all of the information that we know from this study. First, let's write our hypothesis statements. So we have the null hypothesis, which says that the mean of the differences is equal to 0, meaning there is no difference. And the alternative hypothesis says that the mean of the differences is not equal to 0. Now let's write the data values from the difference in times. So And if we have a TI-84 calculator, we would write these data values down in list 1. And once again, don't worry if you don't have a TI-84 calculator. I do have alternate calculators that are built into the problems for the homework. So if you do have one of these calculators, you will go to Stat, and then Edit, and then you will clear out any values that you have in any of the lists, and you will recreate list 1 with the values that are from the previous table, and we're using the values in the last column of that table we saw in the last slide. So I'm just writing those values down here. After we do that, then we go back to Stat, and then we go to the Calc menu, and then we choose one var stats option, and we make sure that the list chosen is list 1, and then we select Calculate, and then we look and see what it gives us. So it should give us an X bar that is 1.75. This is going to be our point estimate. And the standard error follows the formula standard deviation of the differences divided by the square root of the sample size. So in the 1 var stats, it does give us the standard deviation, which is 3.284, and we divide that by the square root of 8 because there are 8 data values. This is approximately 1.161. The degrees of freedom are the sample size minus 1, so 8 minus 1 equals 7. And the test statistic takes the point estimate, 1.75, minus the null value, which is 0, all divided by the standard error, which is 1.161. So this gives us a test statistic that is about 1.507. So if I were to draw a t-distribution curve where 0 is in the middle, we have the test statistic that is 1.507 over here on the right, and we're interested in the area under the curve to the right of that, but also we're interested in the left side, negative 1.507, and we're interested in the area to the left of that mark. So it's a two-tailed p-value. So when we want to find the p-value, we use the tcdf command, and we type in 1.507, 999, 7 degrees of freedom. We multiply this answer by 2 because we are doing a two-sided or two-tailed p-value, and this is approximately 0.1755. Now, since this answer is greater than our significance level of 0.05, that means that we would fail to reject the null hypothesis. In other words, there is no evidence of a difference. Okay, and then just as a reminder, if you forgot where to find tcdf, you would go to second vars and then choose the tcdf from that menu. I wanted to make sure and put that in there. Now, one way that we can check for conditions of normality being met, or conditions of the t-distribution being met is that we can check the z-scores, or same thing as the t-scores because they're the same formula. We can check the z-scores for the maximum and minimum value to make sure that they are not greater than 3 or less than -3. So I'll write that down. Basically, that will help us check for any outliers. I won't do that here, but that's one thing that we could do to make sure that we are meeting the conditions. Here's example 3. A six-sided die is rolled 120 times. Fill in the expected frequency column. Then conduct a hypothesis test to determine if the die is fair. The data below are the result of the 120 rolls. So the expected frequency column, oops. Let's try that again. Okay, so this would tell us that we are going to be using a chi-square goodness of fit test. Okay, so let's go ahead and fill in this table. Now we have the face value that's rolled, the observed frequency of how often that face value is rolled, and the expected frequency. Okay, so since each face value has a 1 in 6 chance of being rolled, then if I roll it 120 times, I should expect a sixth of 120 to show up for each value. So if I take 120 divided by 6, I would expect the frequency for rolling a 1 to be 20 times out of 120 rolls. And that would be the same expected frequency for each value on the die. Okay, now to calculate the z-square, the z-squared value, what I do is I take the observed minus the expected squared divided by the expected. So for this first value I get 1.25. The next one I take 29 minus 20 squared divided by 20, and that equals 4.05. The next one is 16 minus 20 squared divided by 20, and that equals 0.8. Next, 15 minus 20 squared again divided by 20 is still 1.25. Next, 30 minus 20 squared divided by 20 equals 5. And then 15 minus 20 again squared divided by 20 equals 1.25. So what we can do is we can type all of these numbers into another list that we haven't used yet. For example, we could use list 3 maybe if that's blank in our calculators. Also, the chi-square is going to be the total of these values. So let me add those up really quickly. On my calculator, 1.25 plus 4.05 plus 0.8 plus 1.25 plus 5 plus 1.25. That equals 13.6. So our chi-square is 13.6. Okay, so we would do, if you have a TI-84 calculator, you would do Stat, and then go to the Calc menu, choose 1var Stats with List 3, and then choose Calculate. And this is another way that you could find the chi-square if you didn't want to take the time to add up all of those numbers. And so the chi-square is going to be the sum of x. So it'll look like the capital sigma x, and that is also 13.6. So again, this is the chi-square test statistic. So let's go ahead and write down all the other information that we would want to set up. So we're going to write our hypotheses statements first. So the null hypothesis would say that the proportion of rolling a 1 is the same as the proportion of rolling a 2, is the same as the proportion of rolling a 3, and so on. One, two, three, four, five. I gotta have the sixth one in there, and these would all equal 1/6. So we're saying that all the proportions are equal, and also that they're all 1/6. So we're saying that the alternative hypothesis is that not all proportions are as expected. Or we could say at least one proportion is not 1/6. We also know that the chi-square test statistic is 13.6. We know that the degrees of freedom is the sample size, which is 6, or the number of groups, which is 6 minus 1, which equals 5. And then the p-value is calculated using the chi-square CDF command. And we type in 13.6, 999, 5 degrees of freedom, and this gives us a p-value of about 0.0184. Now, since this p-value is less than our significance level of 0.05, we would reject the null hypothesis. This means that there is evidence that the die is not rolling as expected. Okay, and then once again, if you want to find chi-square CDF on a TI-84 calculator, you would go to Stat. I'm sorry, not Stat. You would go to Second VARs and then choose the chi-square CDF from that menu.